In this video, we are extending our one-way repeated measures analysis of variance with the data that we used from our textbook, and now we're doing a two-factor split plot ANOVA. So if you've been checking out the previous video, you saw that we use rater 1, raw score, rater 2, 3, and 4, and we did a repeated measures one-way ANOVA. Now we're going to add in a between group variable. So those variables are within, or occasions, or raters. They are dependent. Now we have an independent or non-repeated measure, which is instructor. We have two instructors, instructor 1 and instructor 2. Every person is rated by all four raters, but now we can also look to see if there's a difference between type of instructor. This is now our split plot design. So we're going to do the same stuff we did for our repeated measures. I'm going to go in and do analyze. I've reset this so that it gives you a second example. We do repeated measures. I can call the within factor whatever I like. In this case, I'm calling it rater, saying there are 4 raters that I'm interested in. If you were doing occasions and there were 4 occasions, you could write the word occasion, or you could write time, and you could say there's 4 times if that's what there were. If there are 3 times, you would write 3. So now I have a within subjects variable. We're calling it rater. If you were having trouble in the theoretical video, the difference between within and between subjects, hopefully this will clear it up. Our within subjects are the different raters. Or you can think about it as we talk about it as occasions. In this case, we're using raters, raw scores, and the between group effect is instructor. We want to see not only is there a difference between raters or amongst raters, is there a difference between the two instructors or instructional techniques they're using. I'm just going to go ahead and put in a couple of these that we've done before. Effect size and power and descriptive statistics, none of that is new to our videos. Neither is looking at the mean differences, and I'll do a Bonferroni correction. You know, for just instructor as an omnibus test, 1 and 2, we can just look at the means. I'm going to go ahead and put post hoc comparisons in here. You can see we can do a Tukey test. We've done these in previous videos and in class. Plots, I will use rater as the horizontal axis, and there's only 2 instructors, so we'll separate the 2 lines with instructor, and I'll go ahead and click add and continue. A lot of that should be recap for those types of add-ons and options that we're using. The big difference here is now we're taking the same one-way repeated measures and we're using a between group variable as well. I'll go ahead and click OK. And I'll go back up. We have our 4 raters, we have 2 different instructors. Descriptive statistics are broken up, rater by instructor. We can even start eyeballing the difference. If you're one of my students, you know that I start to look at means and standard deviations as little mini t-tests or confidence intervals just to start giving me an idea of whether I think there should be a difference or not. So I can look at the difference at rater 1 between instructor 1 and instructor 2 and say just, that looks kind of big. I'm not sure if it's significant, but there's a 2-point difference there. And possibly here, there's a 1.5 difference here. But there may not be any sort of significant difference to that. So we look at the effect. We can first look at the multivariate statistic, which is given to us in our last video. We looked at the Wilks lambda. That is the F value we're going to look at for our multivariate F value. We go across, we see the rater effect, Wilks lambda. Our F value is 74.89. It is significant. The interaction between rater and instructor is also significant. This is kind of our conservative test here. So even if sphericity were violated, the multivariate test doesn't care about sphericity, that assumption. However, it's nice when it's not. So for example, our sphericity test here, our test of sphericity, we can look at the chi-square value and we can see that it is not significant. Okay. We have a 0.55, which is well over 0.05. So that means we can look at the univariate test for within subjects effects. If not, we would probably either report the multivariate F, which there's not that, that's okay in practice as well. But we also might look at, if this were violated, we might look at the lower bound, which is the most conservative test. Because this is not significant, that is, sphericity is assumed, we can look at the F values for when sphericity is assumed. And for radar, for that first column, we see F is 190, it is significant. We see the interaction effect is significant. In our table, for our theoretical model in our slides, we talked about we split up our F table into two sections, for within subjects and for between. These are the two F values that are within subject F values. Radar effect is a repeated measure effect, and the interaction effect is also that random effect because it interacts with the multiple radars. Our test of within subject contrasts. In this case, if you think about this, the radars are not a linear or quadratic effect. If these were time, that might be more interesting. But in this case, we don't really care about the contrast effects. We do, however, this time care about between subjects differences. We want to know whether there was a significant difference by being an instructor. And just instructor as a main effect is F is 4.2 and is 0.086. It is not significant. So even though the interaction came up significant, the main effect is not significant. And I'll skip down a couple things. Our pairwise comparisons, we're not going to do those for our main effects for between groups, because remember, this is your permission to look at the paired comparisons. If this isn't significant, we shouldn't look at the paired comparison. Obviously, this is just the comparison between two groups, but if there were more, we would just stop there with the between subjects effects and look at the main effect of time, or radars in this case. Here are our radars. We've seen this kind of chart in our last video for one-way repeated measures analysis. This really hasn't changed. Everything is significant except 1 and 2. We see radar 1 and 2 are not significant. Everything else is significantly different. The radars are making decisions different than each other. Here are the means for radar. This may be helpful as an eyeball test to look at the interaction effect. We can see that radar 1 and their mean for instructor 1 and radar 1 and their mean for instructor 2. There's something going on. What we would expect, although kind of can see ahead already, is some sort of crossing or divergence to show us some form of interaction effect. And it is indeed the case that although both radar 1 is less than radar 2, is less than radar 3, which is less than radar 4, we can see the increasing score given by radar 1 through radar 4. Radar 4 is the easiest radar. Radar 1 is the hardest radar. But what we also see is that between radar 3 and 4, though, I mean, in general, radar 4 is harder. But now that switches, when we look at when we look at the instructors, we see that, well, it was systematic for 1 through 3. Instructor 1 had higher scores than instructor 2, but we see that green crossing. And for radar 4, instructor 2 is those students get higher grades than instructor 1. That's that crossing effect that we've seen in previous videos when we looked at fixed effects models. And it's kind of neat to look at it here and see that there's an interaction effect going on. But in general, if you were to average out the differences for those instructors, we wouldn't see much difference. And part of the reason why is because when there is an interaction effect, that tends to take some precedence over main effects anyway. That'll wrap up this split plot, repeated measures design, the two-factor split plot ANOVA. And please be sure to check out the one-way fixed effect, one-way repeated measures analysis of variance and other models we've done in SPSS. And I'll be putting out a couple other SPSS videos shortly, which will include some non-parametric tests, and just keep continuing some of these extensions and maybe provide some other examples if you're interested.